Okay, so we need to do a little lecture, quick lecture on the chi-squared statistic because this will be on your final exam. And this is typically normally when I get to the chi-squared statistic. It's usually in the last week or the study week. We have so much information we have to cram into 16 weeks, and I usually don't like to test on this in class, so we just leave it for study week and the final exam. So a little background on the purpose of the statistic. It is involved in what we call goodness of fit tests. And if you're asking, well, what is a goodness of fit test? It kind of runs in the same vein as what we've been doing the last couple of weeks. Remember that when we test population proportions, we use a z-test and we calculate a z-score. This is within the realm of a hypothesis test. And just as we test population means under a hypothesis test, we use a t-test if the sample size is small, and we calculate a t-score. So separately from that, we note that proportion and means, those two hypothesis tests, they come from data that is quantitative. But as we get into data that is categorical, we can test that type of data among counts. We can take counts of categorical responses, like the number of males in a group, the number of females in a group. We have counts there, but the responses are categorical. We can test those group counts using goodness of fit tests and calculating a chi-squared statistic. So we basically use the chi-squared statistic in the same way that we use a t statistic or a t-score or a z-score. So when we use a goodness of fit test and calculate a chi-squared statistic, a common problem would be to figure out if birthdays are evenly distributed throughout the year or are they more clustered in certain months. So scientists might say they believe that birthdays are evenly distributed throughout the year, which would mean that the same percentage of birthdays occur in January as they do in February, as they do in March, April, May, so on and so forth. All right, and we could take a sample and try to prove or disprove whether that is true. Are the distribution of M&Ms the same for every bag? Or is elementary education still a female-dominated field? All of these are examples of problems where we could take counts of categorical variables and then decide on whether or not our sample aligns with a population count. Oh, I have a visitor. All right. So the process of a goodness of fit test, we determine an appropriate null and alternative hypothesis. In the example above, our birthdays evenly distributed throughout the year. We might say that the null hypothesis are birthdays are evenly distributed, and the alternative would be birthdays are not evenly distributed. And then we would take a sample and we would count our responses. We would then calculate the chi-squared statistic and use that statistic with a chi-squared table, which is much like a t-table. I don't have one up, but a chi-squared table has a degrees of freedom column on the left. It has probability amounts on the top row. It has confidence intervals on the bottom row, and in the middle of the table it has a grouping of chi-squared statistics, very similar to a t-table. We would use that table to determine a p-value. We know what p-values are. We can compare that p-value to a predetermined alpha level and decide whether or not we want to reject or fail to reject the null hypothesis. Here is our formula for calculating the chi-squared statistics. So just keep in mind, let me make sure I can ink here. I can draw on, there we go. Keep in mind what that means. That means summation. So we're going to take a bunch of things and add them together. And the formula here is actual count minus expected count squared divided by expected count. And we're going to do this a number of times depending on the different responses that we might have within a categorical variable. All right. The Huffman Institute of Health, here's an example. The Huffman Institute of Health claims that birthdays are evenly distributed throughout every season. A student in an introductory statistics class wishes to test this claim by randomly sampling 100 adults, asking each, in what season does your birthday fall? The following results were recorded. 22 had birthdays in the spring, 21 in the summer, 25 in the fall, 32 in the winter. Would this sample provide enough evidence that birthdays were not evenly distributed? Remember, if we think birthdays are evenly distributed, we should have the same number of birthdays in each season. All right, so let's work through this example. Our null hypothesis would be that birthdays are evenly distributed. This is something that's been put out by the Huffman Institute of Health. Of course, that's not a real institute. And if they are evenly distributed, then we would have the same number or the same percentage of birthdays in each month. The alternative would be that birthdays are not evenly distributed. So then what we want to do is we want to take our sample, and our sample of 100 people saw that 22 were in the spring, 21 in the summer, 25 in the fall, winter, had 32 birthdays in our sample. We also need our expected counts. What would we assume to be true under the null hypothesis? This is our expected counts. Well, if we had a sample of 100 people and the null is true, then the same number of people will have birthdays in each season. So under 100 people, the same should be in the spring, the same in summer, the same in fall, the same in winter. So 25 each would add up to our total of 100 people. Now we calculate the chi-squared statistic. So we look at each individual group. In this group, we have spring birthdays. This represents the group of spring birthdays. We have summer birthdays, and this would be the calculation for summer birthday group. This would be the calculation for the fall birthday group. Remember, it is actual count minus expected count squared divided by the expected count. And then this would be the calculation for winter days. And then we want to add all of those counts together, okay, hence the summation here for our formula. And when we do that, we get a chi-squared statistic of 2.96. And we would take that, and we would look in our chi-squared table for a corresponding p-value, and then make a determination on whether one of those are true. All right, but just keep in mind that I'm not interested in you guys running a chi-squared hypothesis test. We only want to know how to calculate the chi-squared statistic. So up to this point is all we are really interested in. Being able to identify an actual and expected count, throw all of these actual expected counts into a chi-squared formula, and calculate that statistic. All right, that's it for chi-squared. I will be putting together a video shortly about concerning information with the final exam, so please make sure that you watch that today or tomorrow. Otherwise, have a good day.